Part 1. The Cosmic Particle Horizon. First, we will cover the cosmic particle horizon and the observable universe. Our universe had a beginning, the hot Big Bang. Time as we reckon it began with the Big Bang. If there was a universe before our Big Bang, ignore that for this video. Actually, we're going to take time being zero at the end of cosmic inflation, around 10 to the minus 33 seconds after the Big Bang. This will simplify matters without hurting our conclusions, but these results do not apply for the cosmic inflation period. It is believed and assumed that the speed of light in vacuum has been constant at its present value at least since the end of cosmic inflation. Cosmologists use the term radiation for particles and waves that travel at or very close to the speed of light in vacuum as they traverse the vast space of the universe. Electromagnetic radiation, photons of light, microwaves, etc., travels at the speed of light. Gravitational waves travel at the speed of light. Neutrinos emitted in the first second of the universe have traveled at close to the speed of light for much of the age of the universe. It takes radiation time to travel a distance. Since our universe had a beginning and has an age now, we can only see radiation from a finite portion of our universe from the past. That finite portion is called our observable universe. I will make a distinction for light later. Let's consider radiation emitted at time t sub e, traveling the expanding universe and arriving here and detected at time t sub d. For radiation emitted at time tce, traveling the expanding universe and arriving here and detected at time t sub d, the cosmic particle horizon at time t sub d is the proper distance, the actual distance at a given time, given by the right-hand side. The scale factor at time t sub d times the speed of light times the time integral from emission t sub e to detection t sub d of 1 over the scale factor function of time. We will call this capital L sub capital PH, though I don't think there is a standard notation. Don't worry if you're not familiar with integrals or this expression. We will give distances in megaparsecs. 1 megaparsec is 3.24 million light years. In the main course, we considered cosmologists' current standard cosmological model, which gives scale factor A of t and the current age of the universe. I used these to calculate the following results. However, take these numbers as representative for educational purposes, with at most 10% precision and accuracy. Remember, the Hubble crisis is not resolved at present. The cosmic particle horizon now for radiation emitted after the early, brief cosmic inflation epoch is about 14,200 megaparsecs, or 3.2 times the current Hubble distance. This is the proper distance from us now of the original emission points where we would just now be receiving unimpeded radiation that was emitted after cosmic inflation completed. This is the current radius of the observable universe. It serves also for when neutrinos decoupled from matter 1 second after the Big Bang. In the future, cosmologists might be able to detect cosmic gravitational waves from the early universe or cosmic neutrinos emitted 1 second after the Big Bang. Our current observable universe was about 5.6 meters in diameter 10 to the minus 33 seconds after the Big Bang, when cosmic inflation completed. We integrated back to the end of cosmic inflation. Had we integrated back to the beginning of cosmic inflation, we would have gotten an appreciably larger cosmic particle horizon. See the main course section on how cosmic inflation solves the horizon problem. However, there were no photons or neutrinos during cosmic inflation, and the value that we got above is what we want. We could as well have integrated back to 10 to the minus 12 seconds after the Big Bang and would have gotten the same number. The earliest light we can ever see is the cosmic microwave background, emitted 380,000 years after the Big Bang. The light horizon distance now for light emitted at CMB last scattering is about 13,900 megaparsecs. This is the current radius of the visible universe, 2% smaller than the observable universe. Our current visible universe was about 25 megaparsecs in diameter when this light was emitted at CMB last scattering. The light horizon distance now for starlight emitted by the first stars as early as 50 million years after the Big Bang is about 12,140 megaparsecs, smaller than the visible universe. We can use the scale factor to determine the proper distance at the time of emission if we want. As we move the arrival detection time forward into the future, the horizon distances increase because the integrand is positive and because the scale factor increases with time. However, when we reach exponential expansion, the integral saturates at maximum values because the scale factor in the denominator increases so rapidly. But the scale factor in front of the integral continues to increase. This plot is the cosmic particle horizon distance divided by the scale factor in megaparsecs versus time in billions of years from 0 to 140 billion years after the Big Bang. This is the integral times the speed of light. The cosmic particle horizon moves outward faster than galaxies moving with the Hubble flow. As expansion continues, we see more of the early stars and galaxies, more of the cosmic microwave background, more of the early cosmic neutrinos, and more of any early gravitational waves, but dimmer and more redshifted. You can see the saturation when we get to exponential expansion. The final values for the horizons will be approximately 19,200 megaparsecs times the scale factor for neutrinos and gravitational waves, 19,000 megaparsecs times the scale factor for cosmic microwave background light, and 17,200 megaparsecs times the scale factor for light from the first stars, assuming a flat universe, constant dark energy density, the current estimates for cosmological parameters, and no mistakes on my part. So, 100 billion years from now, we will be able to see 35 to 40% further of early gravitational waves, cosmic neutrinos, cosmic microwave background, and early stars, galaxies, and quasars than today, though much dimmer and more redshifted due to continued expansion. You can skip this equation, but it turns out that the rate of change of the cosmic particle horizon with respect to the detection time equals the speed of light plus the particle horizon distance times the Hubble parameter. Here is a graph of the derivative for the first 30 billion years of the universe. The derivative is twice the speed of light in the early radiation-dominated universe, where the cosmic particle horizon and Hubble distance, which we cover next, are equal. The derivative increases with time and scale factor as radiation gives way to matter, and later, matter gives way to dark energy, and is infinite at infinite time in the exponentially expanding universe. The cosmic particle horizon recedes faster than the speed of light and faster than the Hubble distance recedes. As the universe ages, we see more of it, more of the early universe, more of the early stars and galaxies, more of the cosmic microwave background, etc. But the cosmic microwave background is already remarkably uniform in all directions. How this can possibly be is called the horizon problem. In the main course, we covered that cosmologists believe there was an early, brief, but important period of extreme, faster-than-light cosmic inflation in the early universe, such that all of our universe that is within our far future particle horizon was in causal contact and thermal equilibrium before cosmic inflation. This completes the section on the cosmic particle horizon.